AUV Challenge final presentation by
Advik, Kunta.
Brandon Wang.
Ethan Chen.
And Shaunak Roy, and we are the West Coast Best Coast.
So, our overall goal is through using image processing, our AUV will be able to navigate through an adaptable course that are indicated by light-up buoys.
When designing autonomous systems, we should be able to relate to it the most, as we ourselves, human bodies, are very efficient and successful autonomous systems.
Naturally, as we would with tasks for human body in real life, we always start with observations. And to make observations, we need sensors to be able to collect data from around us. For example, human eyes are essentially camera sensors. We are continuously getting images from our surroundings, which we then later use to process and analyze to draw conclusions regarding the size, color, and shape of an object. This is basically what we did when we were trying to work with sensors with our AUV. We had access to a Raspberry Pi camera, which we used to collect periodic images of what buoys lay in front of the AUV, so that we can successfully pass through the gates.
Once we have the data we need to analyze, the next step is to actually analyze it. This is similar to how our brain analyzes observations that our other senses might collect. Bringing this connection to a more relevant situation, the optic nerves in our eyes transmit these images from our eyes to the brain. The brain then processes these images by actually determining the shape, color, or size of any and all objects in the system. Similarly, the Pi camera takes the images, and then another buoy detection module in our code acted like the brain in the situation and analyzed the images and returned the horizontal angles to the buoys and also the colors of the buoys along with that.
The next step would be with making a decision based on what we see. Depending on the objects that we see, our brain might require us to react differently. If we are driving a car and see a red light, the decision we make in our brain would be to stop the car, or more specifically, put your foot on the brake and press down. Similarly, the code would analyze the images and decide how to position the rudder to make the AUV travel in a certain direction.
After receiving information from the autonomy logic, the vehicle would do actual actions and perform actual tasks like rotating the rudder or increasing the engine speed. This is like when you think you want to raise your hand, then you actually do it. Splendid. Sometimes it doesn't always work the way you want it to, but in the end, your vehicle would listen to your brain and carry out functions as specified by the brain. This is like our vehicle control in the AUV, which would take in bluefin messages from the autonomy logic functions and then change the rudder angles or engine speeds to actually control the hardware. These are like our legs that actually do the walking function that the brain wants us to do.
So here we have a hypothetical setup of the AUV. This is the AUV, and these are two buoys, the red one and the green one. And so right now our image processor would have matched the red buoy and the green buoy. And what the AUV will try to do is turn towards this gate to pass through it. But we want to pass through it specifically perpendicular, so along this line. So after it passes through, it'd be heading straight this way. And the reason for that is because the AUV only has a set HFOV, which is horizontal field of view. And so if we pass through at too sharp of an angle, say along this line over here where my pointer is going, then it would only be able to see from maybe here to here. And so if any buoys were over here, then we would have no chance of seeing them. If we pass through perpendicular, then we would see both on top and on bottom to the next buoy. And so the first step it does in calculating the turns it has to make is drawing a line from the furthest buoy, which in this case is the red one, to its current position and taking the midpoint. And so now we have a point. We have a point here and a point where the AUV is currently at, and we have a tangential line, which is the current heading of the AUV. And using those three parameters, we can calculate a circle. And from that circle, we can calculate radius, and using the turning rate of the AUV, which is given experimentally, we can calculate what we have to set the rudder to in order to turn along this circle. And so right now it would give a command to set that rudder and then begin turning along this circle. The next step, after a set point of time, it would run another set of code, which this time it sees that it does intersect, the current heading does intersect with the perpendicular line. And so it would draw another circle. And this time it would draw a circle with these two being tangents and this point or the current point of the AUV being a point that the circle has to pass through. And so now we have this new circle. And so the AUV would go in a straight line towards this point on the circle. And then once it reaches this point, then it would start turning. So it would set another rudder. This would give us a relatively like S-shaped path that our AUV will take in order to go through the gates perpendicular. Yes.
Let's try Brandon's logic in this simulation. As you can see, with our successful run, we were able to clear 50 gates with Brandon's logic, in addition to conserving a lot of battery. One of the most important parts of autonomously controlling your AUV is communication between your programs. All of your programs require each other's information in order to do their function. One example is in order to detect a buoy in the buoy detect function, the function needs an image from image processing in order to do its job. Another example is the decide function needs the conditions of a buoy detect function in order to make a decision on where to go. Next, is logging. In order to communicate with the other files, it's important to store the information somewhere so the other files can know where they can read the information from. And with those, we were able to test this in real life. So as you can see, our testing was all right. We were able to move our AUV in a straight line, and we passed the first gates by turning autonomously, which is great. Unfortunately, after reviewing what our files and our logging, we realized our image processing didn't was exporting bad images, which resulted in us not being able to pass the most of the gate at the end. And in addition to that, our program was kind of difficult to debug because it was setting one error while it was probably a syntax error from somewhere else. Uh, Thank you to everyone who made this possible, especially our teachers, Joe and Madeline, and our TAs. And we hope to continue learning about this field in the future. Thank you.